Okay, so in this video, I want to talk about Pascal's triangle. Right now, what exactly is Pascal's triangle? So it's a very easy to generate. Right, if we have one, so usually we start with one, one. So it says one thing that we'll see here is we'll start counting at zero. So that's the zero row is one, and at each row we increase the number of elements by one. Now the way we do that is we always start with one, and then the next one, starting with the second row, is the sum of the two above. So up here we get 1 plus 1 is 2, and then we end with 1. All right, and then the same thing here, 1. Right, this next one would be the previous. If we look above, 2 plus 1 is 3. The next one here, look above, 2 plus 1, 3. And then we end with 1. Right, so always kind of bookended by the ones. Now, here's a nice visual to kind of get a better look here at what I'm talking about, what I'm drawing there, right? So here we have our Pascal's triangle, right? And if we click on any element 2, you see it highlights the 2 above, that gets you that number. All right, so if we go down here, right, let's look at this 5 right here. So this will be in the 0, 1, 2, 3, 4, 5, the 5th row, right? And again, always counting at 0, 5th row, 0, second element in there. Or excuse me, first element, right? 0 element, first element. We click on it here, and then we see it is the sum of the 2 above. And as you can see here, right, 1, it just always is 1, right? You know, you can think of just 1 is only 1 above it. There's none in this space here. 5 here is 1, 4. All right, and then see 10 here, 4, 6. So the other 10, 6, 4, 5. And you can see there's a sense of symmetry here as we kind of move along with the numbers as well. Now this triangle was kind of created very basic, right? You can kind of, it's an infinite triangle, really. You can just keep going, you know, on and on, just adding rows, right, by increasing the elements by exactly 1 at each row. But as it turns out, doing something like this provides a variety of different just patterns, things that kind of show up here, right? Here's something that we have here where if you look at what's highlighted here, it's just the multiples of 2. And then you could see that they're not just really randomly placed on the triangle right here, even though, right, the way we created the triangle is just kind of very simple, right? It turns out there's a lot of structure in this triangle here, right? If we kind of just flip the elements around, you see there's a sense of shapes being built, right? Kind of patterns that evolve that you wouldn't necessarily expect of just how we started this this triangle here, right? Now, here's another one here. I guess all different kinds of things that kind of show up here. I think one of them I found interesting here was here the powers of 11. So here, as it turns out, this will work up to the 5th row, right? 11 to the 0 is 1. 11 to the first power is 11. 11 squared is 121. And 11 cubed is 1,331. All right, so that's just kind of a pattern that just kind of shows up. Another interesting one here is where is it here? The powers of 2. Now this one just works indefinitely here as the further off we get going. So this one here, it's all you have to do is sum up the row, and that gives you the power of 2. Right, again, always starting counting at 0. So 2 to the 0, 1. 2 to the first power is 2, so that's 1 plus 1. 2 squared is 4, so 1 plus 2, 3 plus 1 is 4. 2 cubed is 8, so 6, 7, 8. Excuse me. And etc. Just kind of moving along there, right? And then also one Here's another pattern here, the triangular numbers, right, where you can make the a triangle here out of rows, right? 1 makes a triangle, and then 3 where you have a row, 2, 1. So where you have this general setup, right, these are called triangular numbers. Now, as it turns out, that is here, this diagonal here, that 1, 3, 6, 10, those are all are triangular numbers. And here, one last one here, or a couple one here. As it turns out, if you just shade the odd numbers, and as you see here, you get this fractal pattern that emerges here, right? So if we zoom out, right, and we continue doing this, we could see that the further we zoom out, we just keep seeing this triangle reemerge, that pattern, right? It's a fractal. So also just kind of an interesting pattern that arises here. And then lastly here, the hockey stick. So as it turns out, by starting at 1 on other side, any side, I should say, right, on either side here, and you just kind of stroll along the diagonal, and any number that you want to stop at, just make a turn, and that number will be the sum of the previous diagonal that you have here, right? So you see 2 examples here, right? 1 plus 6 plus 21, 28. 1 plus 3 plus 6 plus 10, 20. All right, and we can keep going here, right? 20 plus 15, then make a turn here, 35. Right, above here, 15, 35 plus 21, 56, and so forth. All right, so just lots of different patterns here that show up here. Now, one thing that is useful here in algebra here, if, for instance, let's say we had to do something like this. Now we could FOIL this out, and what we'll get is this here. All right, now I'll write this here so we can see the pattern here. A plus B cubed. So as it turns out, this is 1. That's A squared. A cubed plus 3. A squared B plus 3 A B squared plus B cubed. So if you were to expand this to the 3rd power, you would come up with this expression here. And what we notice here is that if you look at the coefficients there, 1, 2, 1, 1, 3, 3, 1, those are the numbers, again, corresponding to the row here, 2, 3, right? This is that 3rd row there, right? Those coefficients are what we call the binomial expansion coefficients, right? So if you needed to do something like A plus B to the 5th, right? You can do that very easily here, like looking at this one, the triangle here, 1, 0, 1, 2, 3, 4, 5, right? So these would be the coefficients. 1, 5, 10, 10, 5, 1. All right, now how you expand it here, you can also notice the pattern here, right? The first term is always A to the 5th, the largest power, and each step of the way, the A goes down by a power of 1, and the B increases by a power of 1. The whole time, the sum of the powers is 5. All right, and each step of the way it was 1. What were those numbers? 1, 5, 10, 10, 10, 10, 5, plus 1. Okay. So now provides us a very fast and easy way to expand this, right? Excuse me. Okay. All right. Now, another useful thing about this Pascal's triangle is in the notion of what are called lattice paths. So here, let me recolor these. So if we think of this grid here, right, which we can label 0, 0, and then here we'll go 1, 2, 3, 4. All right, so 4, 0, and this one up here, 0. All right, and the idea here is if we want to count the shortest path to get from one point to any other point on this grid here. All right, so let's say this was point A and this was point B. All right, now as we can see, there are a lot of different ways I can get to B here, right? The shortest path, right? I can go this direction, that's one. I can go this direction. I can go this direction. And I can go this direction here, or this direction here. Right, so those are the shortest paths to get from A to B. So as it turns out, there is an easy way to count this, right? And it involves Pascal's triangle. Now, if I take a look here in our textbook, right, we could see kind of the overlay. If we kind of slant our grid here, right? And to get to whichever point, if we interpret that as being on the Pascal's triangle, whatever number I land in, that is the number of paths there are to get from this point to this point here, right? Now there's a good algebraic way to kind of do this, and we'll get into it later when we talk about the paths taken here. But the way you would do that, or excuse me, the n choose k number here, but the way we would do this here, and here I'll show you here for now, right? So if we look here, if we look at this, our lattice path here, so 0, 0, and the point here would be 4, 4, 3, right? So you want to determine how many different paths there are to get from here to 4, 3. So expanding that here, if this were 0, 0, up here. All right. So if we were wanting to find out how to get from 0, 0 to 4, 3, so as it turns out, what we can do here is we can add these two numbers, 4 plus 3, and that equals to 7. So this tells me to look at the row in Pascal's triangle. All right, and so 7th row, and now that I'm in the 7th row, so looking at this here, right, so keep this in mind, right, this says 35, but where did that number come from? So go to row 7, so 0, 1, 2, 3, 4, 5, 6, 7, all right, and then it says, so once I'm there, now the coordinate was 4, 3. Now, it actually doesn't matter which one of those you choose. Either one is going to lead you to the same result here, right? So if we take a look at the third element, okay, so again, count at 0. Start counting at 0. 0, 1, 2, 3. 35 different paths. Or 4, again, 35 different paths, right? It's that symmetry here, all right? And going back to our lattice, you see here, to get to 4, 3, that's where that number 35 comes from. right? So you add the two coordinates, and then to pick which element in that row of Pascal's triangle, right? Then it's either one, 3 or 4, right? So look, going back here, row in the Pascal's triangle, and then the 4th or 3rd element. And again, don't forget, start counting at 0.